Good morning, good afternoon, and good evening, everybody. Thank you for joining this webinar on Load Balancing 101. What is a load balancer? My name is Frank Yu. I'm the Principal Application Experience Architect at Kemp Technologies, and I'm going to go through a presentation to give you some good ideas, hopefully, on why we have load balancers, what they do, how they work, and little technical aspects of how it actually works. What is the underlying technology and what is it good for? So as I go through this presentation, please ask any questions that you have. In your window, you should have a question mark where you can submit questions and provide them, and I'll be more than happy to provide a Q&A session at the end of this presentation to give you anything. So I look forward to seeing your comments and your questions, and let's get into this presentation. So again, load balancing 101. What is a load balancer? It's a good question, and there's a lot of things about the history, and there's a storied history of load balancing technology and why we have it and what it does for us. And let's really start thinking about, why do we have load balancing? And I'm going to go back let's turn back the clock. Let's go back to a different era. And I'm going to go back to the mid 90s. The internet has started to become popular. www, HTTP web services, this World Wide Web. We don't really use that term anymore, but this World Wide Web is becoming really popular back in the mid 90s. And we have lots of users starting to connect to this thing called the internet and connecting to all these sites and servers, these sites hosted on servers. And ultimately, we found that there's a problem. These servers weren't big enough. They could only handle so many connections, and we had more users than we had capacity on our servers back then. So you might have these users, and you might be saying to yourself, you know what? I have these people coming to my website, and this is really good. This is fine. And I love this comic. And it's kind of representative of 2020, but this is fine. Everything's coming to my web server. I'm getting traffic. My web server is chugging along. And then, the next thing that happens is I put something else, some other type of content. I might be e-commerce, and I have the hot new gadget or toy for the holiday season. Or I have this great controversial blog or something coming up on content. And you know what? Next thing you know, you have a lot of people trying to get to this web server. And you know what happens to that web server? It is no longer fine. It is falling over in terms of capacity and support. And we really didn't have a very good solution to deal with this problem. How do you get all these users to get to my site when my infrastructure, my hardware, my CPU and memory and network couldn't handle that capacity? So this was a problem. We need to get this resolved. And there was another problem. Things break. Stuff happens. That is a safe work version. Stuff happens. So we have all these people going to this website, and everything's happy, everything's chugging along, and things are going great. And I'm thinking, I'm king of the world. All these people coming to me, I'm getting popular. I got my 15 minutes of fame, or I'm making money because I'm in a business. And people are saying, this is great. But you know what? As we all know, hardware, software, bugs, failures, things break, fiber gets cut, things overheat, fires, who knows the case. And next thing you know is this is your server. It is going underwater. It hit something that you did not expect. In this case, it might have been an iceberg. I don't think there are icebergs in data centers or in your homes. I hope not. But things can happen and it'll fail. The hardware, software will fail, and we didn't have a very good way to get people to go from a site that was broken to a version or instance of that site was available. So we need to fix these problems. These were two of the primary problems that we were trying to fix with load balancing technology by introducing load balancing technology back in the 90s and through the 2000s and up to today. So load balancing technology has been around for a while, and it's getting pretty mature, and there's some really cool things that we can do. So what is load balancing doing for us? Load balancing is really solving, number one, that first problem, scalability. How do I scale my application, my web server, my website, my system so that I can accommodate the number of users I have. And this could be a problem. For example, you might have situations like Black Friday, e-commerce, very popular today, Cyber Monday, where e-commerce becomes very popular and you need to scale and you don't have the resources and you need these resources quickly. Now you need to be able to add them and do it in such a way that the users aren't impacted on having to look up new names or addresses and still get to the site and get to the things that they want. Load balancing can solve this. Number two, that availability. How do we know when things fail? And if something fails, how do we know and how do we get the technology to redirect the traffic to instances of that application that are available, that work? We need to make sure in an easy, convenient manner, and ideally in an automatic manner, that things are working. And of course, all this gives us this concept of agility, this flexibility, we talk about agility. We talk in today's technology world in terms of like digital transformation, cloud, software defined, all these buzzwords. But really what it means is that we have the ability to quickly change things and adapt to the current environment as that environment evolves. So we need to fix this. We need to get that ability to be able to make changes without impacting the user, without making changes that they have to do things differently, put in different URLs in their browsers or anything like that, and make it easy for them. So we want to provide that agility, and that agility gives us that scalability and that availability in those other pieces. So how does this load balancing work? First, let's baseline ourselves. Load balancer. What is a load balancer? And like using the term cloud or digital transformation, I could probably ask 10 people and I'll get 10 different answers. But here from Wikipedia, our internet version of the dictionary, the load balancing refers to a process of distributing a set of tasks over a set of resources, such as computing units. That's a pretty good definition and is a pretty broad definition. And it can apply to a lot of different things. And here you might see different terms being used for load balancer. You might hear of it being called a reverse proxy or a network load balancer or application load balancer. And all these are subterms or other terms that we use to define exactly what we mean when we talk about this load balancing technology. Because it is a solution that sits in the network. It can sit as software, it can sit as hardware, but it sits in the network. So it is load balancing at a network perspective. And we'll see how that works as we go through this presentation and the technical details. And we are load balancing applications. It is all about applications. It's not about the plumbing. We don't care about the routing tables. We don't care about the VLANs and the network layer of things. Well, we kind of do, but we are focused on this application. And this concept of a reverse proxy. We are acting as that interpreter between the client and that server and that or the application. And we are acting as that proxy. And we say reverse proxy because we are proxying for the application versus proxying for the client. If you're proxying for the client, that's a forward proxy. So we're a reverse proxy. So these are terms that you'll hear, but ultimately we can bring that all together and say that we are a load balancer. We are providing load balancing technology. This is a load balancing solution. Fundamentals. The core basic function of a load balancer is what we call server load balancing. The server load balancer, or SLB, is a reverse proxy. It's managing pools of application servers. So here you can see in my diagram, I have the clients at the top of the diagram. I have my load balancers in the middle with that icon on them. That icon is a generic icon to represent load balancing technology. And underneath, I have my real servers, my servers with the applications being hosted or running on those servers. And here's a couple terms that are important for you to know. We have this concept of VIP, virtual IP, or is also commonly referred to as a virtual server, VS. So this Virtual IP is an IP address that's hosted on the load balancer to represent the application. This is that reverse proxy concept. We being the load balancer, are hosting that IP address for that application so that all the clients will connect to that virtual IP address. They're connecting to this IP address that the load balancer is hosting. And then the load balancer is taking those connections and passing them on to these RS or real servers. These real servers have their own IP addresses, their own applications, but the load balancer is smart enough to know what those IP addresses are and what the applications are that are being hosted on those IP addresses. So we will tell the load balancer, this VIP is associated with these real servers for this application or this set of applications. And the load balancer will do the distribution. So, for example, we have the client connecting to a real server through the VIP and making that connection and accessing the application online. This could be you doing this through this Bright Talk presentation right now, where you're going to this website, listening to this presentation, listening to me and watching this and making a connection. And there's a very good chance there's a load balancer in between managing that connection for us. And of course, if that application has a problem and it fails, hardware or software is just not able to connect to it, the load balancer needs to be intelligent enough to understand that and say, okay, stop sending connections to that instance of the real application on that real server, and instead send it to a different instance of the application that is available, that is working. So that helps gives us that availability for the application. This should be all done automatically, this process, by the load balancer to make things efficient for the application access for the clients without the clients having to make any sort of changes. So this is the cool part, is that the load balancer is doing this automatically, and it manages it. It manages connections, manages the availability. And how is it doing that? What is the technology behind that? What is driving this to make this actually work? Let's open up the hood a little bit and take a look at how this application works. So fundamentals. First, this load balancer has what we call a connection table. It is acting as that reverse proxy. It is managing the connections between the client and the load balancer and the load balancer and the server. And that connection table is based on what we call a 5-tuple. In other words, there are 5 parameters that the load balancer uses in its table to identify and distinguish each connection to make them unique so that it can manage them all properly. Those 5 fields typically are going to be source IP address. What is the IP address of the client? The second is the destination IP address. What is the IP address that the client is trying to get to? This is usually going to be that virtual IP address, at least on the front side of the load balancer. The third piece of information is that source port. So if you know TCP and UDP, they have ports. These ports range from 0 to 65535. Oh, I see I have a typo there. It's 65535 in the port numbers, and it's going to be typically the source port is going to be something above 1024. And then you have the destination port, which is the port that the application is listening on. And then last is IP protocol. This is something that's not commonly talked about in the tech industry and by the networking folks, but IP protocol is very important. For example, how do we know if a connection is TCP? Is it UDP? Or is it some other protocol? Because there are other IP protocols out there besides TCP and UDP, if you can imagine that. And the most common IP protocols in this case, and obviously, are going to be TCP, which is IP protocol 6, or UDP, IP protocol 17. And here's something that's going to be useful for you. Here is a table of commonly used ports at the application side of things. So that destination port is usually going to be a port number that you know and you recognize it. It has to be because it's going to always be listening on those ports. So, for example, I'm not going to go through this entire list, but you can see, for example, HTTP port 80. HTTP, which is the web protocol, port 80 is the most common port used for it. By default, everything is going to be on port 80. Alongside that is HTTPS or HTTP secure, those encrypted connections. And you can see at the bottom of that list, port 443. Port 443 is going to be for HTTPS. And then you have other protocols that you may or may not know about, like DNS for the name lookup from the names to the IP addresses. It's going to be port 53. I don't say whether it's TCP or UDP because it varies. For example, HTTP and HTTPS is going to be TCP. DNS, it could be UDP, usually UDP, but it could be TCP also, depending upon the context. And then you have other protocols like SNMP for network management, port 161. You have like if using Exchange, Microsoft Exchange for email, authenticated SMTP 587 is a common port that is normally used for that. So you see, you'll learn as you start looking at this technology and building configurations and understanding applications that they use well-known and common ports. And you can see, just FYI, that all these ports are less than 1024 because most of the well-known ports, I'm not going to say all, but most of the well-known ports that are used for applications are in that lower range of numbers for those destination ports. So if you see a port that's less than 1024, well, it's probably a predefined, well-defined port for that application. This diagram looks complicated at the beginning, but let me break it down for you. So here at the top, you see the client, the load balancer, and the real server from left to right. I put the IP addresses, the C for the IP address of the client, the VS for the IP address of that virtual server or the VIP. And then we have a load balancer address on the right-hand side for the load balancer as well, and an IP address for the real server. Now, when we make connections, and let's start looking at those yellow lines, this is a TCP connection. I can see that on the left-hand side, I'm starting with a port of greater than 1024, less than 65535. So it's a random high number port. It's TCP, and I'm going to port 80. In other words, this is most likely going to be HTTP web service. And then on the right-hand side, I have other information to the load balancer making connection to real server. Again, high random port to port 80. And you can see that the source and destination, the S:D, of these connections are different between this load balancer. The load balancer is acting as this interpreter or translator, where it's taking the connection, source the destination from the client to the virtual service, and then translate it to the source destination from the load balancer to the real server. And then let's look at this packet flow real quick. So TCP protocol, the standard opening for the protocol is to do what we call a three-way handshake. SYN, SYNAC, ACK. The client sends a SYN, server sends a SYNAC, and then the client sends an ACK to acknowledge that, to do this three-way handshake to say, yes, we're ready to establish a connection to make it happen. You can see the load balancer does not do anything to the server until that handshake is done. When that handshake is done, then the load balancer will make that full three-way handshake to the real server itself. It does this to protect the server in case the full handshake is not done. It wants to make sure a connection is definitely going to be established before it does anything to that server. And then the client starts sending data back and forth. You were surfing the web page, doing lots of things, getting content back and forth. And then there's the closing of the connection. The fin close, the four-way close, the TCP connection process for closing the connection, and the load balancer will manage this on both sides. So it's managing really two connections in that connection table, one between the client and the virtual service, and two between the load balancer and the real server that it determined to make that connection to. As we go through the rest of this presentation, kind of keep that concept in mind, because this is going to become, this is a core component of how the load balancer works and what it's doing. So let's talk about how the load balancer makes the decision to do this traffic distribution. If there's a pool of servers that host the same application, how does it know and make a decision to send traffic to one server versus the other? And there's traffic distribution algorithms. We have these methods, and there's a whole slew of methods, and different vendors have different ones. And these are some of the most consistent ones that you're going to see, where we have things like round robin. Round robin is exactly what it sounds like. It's eeny, meeny, miny, mo. Send it to 1, 2, 3, 4, back to 1, 2, 3, 4, and keep on rotating, rotating, rotating. Weighted round robin, where we do some weights. We'll talk about the ones that are bolded in a little more detail. Weighted round robin is a little more specific to the types of servers. Then we have something called least connections. That's based on the capacity of the servers, the current load. We have weighted least connections. We have something called an agent-based adaptive load balancing. This is where we can do provide some sort of agent on the server or application to say, okay, based on what you see, you tell me if you're available to make a connection, and I'm then going to make a decision. So getting more application or server specific information. Fixed weighting, weighted response time. So when we talk about more, we'll talk about how the load balancer determines how healthy the server is, and we'll see things where weighted response time can come into play. And there's even something called source IP hash, where it actually takes the client IP address, does a mathematical method such as divide by 256, give me the remainder. This is what we call like a mod. In mathematical terms, we call this mod 256. Give us a mod 256 of the IP address, and based on that mod number, it's going to be allocated to a specific server. So there's lots of cool things and interesting things that we can do to determine which server to send the traffic to. And let's go into detail to give you some examples of how this works. So round robin, again, very straightforward. A, B, C, D, A, B, C, D, A, B, C, D. So connections come to this real servers, and it's going to just sequence itself along. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and keep on rotating through all the servers. Of course, that's assuming all the servers are available. And we'll talk about the health checking and availability here in a minute, but it just round robins through the sequence. Weighted round robin is very similar. It's going to sequence through the instances of the applications, but we can assign specific weights to those instances. And this may be due to resource capability. One instance may be sitting on a server that's newer, that has more capacity. So it can handle more load than the other servers, and I want to distribute that load appropriately. So here you can see I have 4 versions of the application. They have a weight of 1, 3, 1, and 2. In other words, the one with 3 is going to get 3 connections for every 1 that the other servers get. So weighted round robin, when I send those connections, it's going to go 1, 2, 3, 4, 5, 6, 7, 8, etc. So I'm going to load balance through those applications, through those instances of the real servers and the applications, but I'm going to weight them based on my configuration and how I define the weight. Again, very straightforward, is very consistent once you apply those weights. Least connections. This is something that is probably the most common and usually the most recommended way of doing load balancing for how you determine the traffic to the servers. The way this works is that we actually monitor, because we have a connection table like we talked about. We have a connection table in the load balancer that says I have X connections to this server, Y connections to that server, Z connections to this other server. So I know how many connections there currently are going to these servers. And one thing that we've learned about the internet and web traffic and traffic in general is that they are not consistent. Some connections last a long time. Some connections are very, very short. And even for the same application, even for the same user, the length of those connections are going to vary. So if a connection comes in and quickly dies, then that server should have that resource available for a new connection. So we can look at the number of connections going to those servers and send the traffic to the instance of the server in the application that has the least number of connections going to it, therefore calling it least connections. So here it starts like round robin. 1, 1, 1, 1, 2. So I've started, I have 5 connections. They've gone through 4 instances of the application, and the 5th one goes to the second one. During that time, I might have a situation where, you know what? Somebody stops using the application. So now there are 0 connections on that instance of the application. The load balancer knows this, and it's going to say, you know what? There are now 0. That is the least number of connections in my list of application servers. I'm going to send my next connection to that instance. This is how load balancing works with least connections. And again, it's most commonly used and recommended because it gives us probably the best distribution in terms of availability and managing the resources on those application servers. So it's highly recommended. Let's talk about health checks. How does the load balancer know if the application is up and running? How does the load balancer know if the application is actually healthy? How does the load balancer know that somebody did not turn the power switch off on the server? And it's going to do health checks. And this is an industry standard term for what the load balancer does to manage these connections and access to these servers. So what is a health check? Is a connection being made from the load balancer to the servers in the application to ensure the application availability. And they range from layer 2 to layer 7. They increase the layer as you go up that OSI model from layer 2 to layer 7. The intelligence and the insight that load balancer gets is going to be increased in terms of what it understands and knows. So the load balancer will ask basically the load balancer is asking, are you okay? In different forms. And hopefully the server and or the application are going to respond and say, yes, I'm okay, or I'm not okay. Or if it doesn't respond, that could mean that, it's not available and something's going wrong. Let's look at the different types of health checks that we commonly see with load balancing. First is this layer 2-3 health check. Fairly straightforward, standard networking technology. The first piece is address resolution protocol, the ARP. And then within this layer 2-3 model is ICMP. This concept of ping. Send a poke and hopefully get a response. Send an echo and get an echo reply. So if we were to look at the ARP, for example, the load balancer is going to send on the network standard networking technology. I'm looking for the IP address 172.16.1.101. Somebody help me out. Somebody on the network tell me. This is a layer 2. This is a broadcast from on the network as a layer 2 message. This is an ARP request. And the server is going to respond. I am IP address 172.16.101. And by the way, my MAC address, layer 2, is in this case 00:14 EE091CE3. I think that's actually my laptop MAC address for this presentation, but it's the MAC address of the actual server. So now the load balancer knows that this IP address exists on the network and it is reachable through this MAC address. Same thing with this ICMP is I have the ARP entry. I have this entry of MAC address IP in the table. I'm going to send pings, ICMP echoes on a regular basis to make sure that it's still available. By the way, these health checks are run by the load balancers usually on the order of about every 5 to 30 seconds, depending upon how often you want to do it and what the purpose is and things like that. But about every 5 to 30 seconds is typical for load balancing health checks. Let's move up that OSI stack. Layer 4 health checks. So layer 4 health checks, I'm talking about specifically TCP and UDP health checks. How do I do a TCP health check? Well, the answer is kind of easy. I'm going to do that 3-way handshake. The load balancer is going to send a SYN. The server should send a SYN-ACK. So I'm sending a SYN to, say, for example, TCP port 80, because this is an HTTP web application, right? The server is going to send a response saying, yes, I'm listening on TCP port 80. I have an application listening, and I'm going to send a SYN ACK to say, yes, I am available. And the load balancer will then send an ACK saying, yes, thank you very much. We're ready to make a connection. But then for the health check, we're going to close the connection at that point. There's nothing else we need to know. There's no data. There's nothing. All we want to know is the server is actually listening on the port and is ready to accept connections. So we're going to close it using the standard TCP close, or maybe even send a TCP reset, which is a hard way to say, I'm done. I'm not doing anything else. UDP is slightly different. If you recall your networking technology, UDP is connectionless. There is no connection table. There is no handshake. It's just send data and assume that it gets there and assume you get a response. So how do you do a health check for UDP? We send what we call a datagram, which is a packet. In UDP language, we call it a datagram. We send a packet to that UDP port. So if it's DNS, we're going to send some sort of data to UDP port 53. If the server is listening on that port, it's just going to take that data, and if it responds, it responds. If it doesn't respond, it doesn't respond. The load balancer really doesn't know if the server is actually responding or listening to that port. But if the server is not listening to that port, the server will send a UDP unreachable. It will say, I am not listening to that port. Stop sending me traffic to that port. So the health check is kind of actually inverted. If it sees something from the server, it says, I see UDP unreachable. You're not available. I'm done. Otherwise, if I don't see anything, and there's a timeout because we have to say, okay, after how much time of me not seeing anything, do I assume things are good? The timeout is usually, again, 5 seconds and it's configurable. But then we assume that the UDP port is being listened to and is available on the server. So these are kind of good for the layer 2, layer 3, layer 4, but we still don't understand anything about the application. What is the health of the application? Is the web server healthy? Is my DNS server running? Is it actually responding properly? How do I know what's going on? And we can move up that OSI model. So now we have layer 7. We can send application-specific data to the application and server. Usually we send an open connection, like a TCP handshake, and ask for something basic, and we get a status code in return. Or we can actually send something completely custom. This custom thing could be anything that we want, where we send any data, we receive data, and we can inspect that data to determine what we want to do. So let's look at an example here. And I'll use HTTP since it's the most common application. Most people know HTTP on how it works. The load balancer is going to send its TCP handshake, the SYN, SYNACK, and ACK. And then it's going to send its HTTP request. In this case, HTTP get/HTTP/1.1. This is a very standard HTTP request to get the page for a web server. And if the web server is listening and understands and it has something to deliver, it's going to send some sort of response. The standard response, part of the response is going to say HTTP/1.1. I'm assuming this is HTTP protocol 1.1 versus 1.0. It could be 1.0. But the key thing here is what we call the status code. This status code is 200 OK. 200 means that I am happy, I am listening, I am a well-behaved web server application, and you can send me things, and here's my return. So looking at the status code becomes very important. Other status codes might be 300 series, 301 or 302, which is an HTTP means it's an HTTP redirect. I'm listening, but you're going to the wrong site. You should go to this instead. Or you might get the dreaded HTTP 404 status code, page not found, or 503, server not available. In other words, it might be overrun. It just can't handle the request for some reason, but there are multiple status codes that it can return. And we're going to look for standard status codes that say things are healthy. And this is configurable to say, in this case, for example, status code 200. And these status codes, interestingly, us being the internet engineers and designers, have tried to make things somewhat standard. So when we look at other protocols like email, SMTP, Simple Mail Transport Protocol, the status codes are going to be very similar. We're going to look for status code 200, which means okay. So in general, if you see status code 200, okay. And again, if you want to create a custom health check, you can do that by sending specific data, and you can even then check for a specific return. For example, I could check for this 200 okay in this return, or I could check to make sure it's HTTP 1.1 versus 1.0. I can customize how I do these health checks at layer 7. I can be really flexible, and this really gives us an understanding of, is the application available? Because this is one of the key pieces. It's not just, is the server online? Is the Apache web server actually up and running? But is the content and the delivery of the service that we're trying to do actually feasible and working right? And that's what these layer 7 health checks can do. So highly recommended that when you use load balancing technology, to incorporate those layer 7 health checks to get as much intelligence about the health of the application as possible. There are other uses for load balancing technology, and I don't have time to go through all of it. But there are things such as content switching. Content switching, where you can use the load balancer because it's managing that connection, is inspecting those requests and those connections coming from the user. It can actually make decisions based on what we see in the content. For example, I could set up a web servers with different instances to say that's one of my web servers, you can see in this diagram, can be what I call my image server. Anything with JPG or PNG or TIF will go to this server. Dynamic content, anything that has PHP or .NET or ColdFusion.cf, I go to a different set of servers. Excuse me. And I can even set it up so that I have different paths. So anything that's going to any file or anything within the subdirectory /files, I can send to a different server. So I can do inspection and this content switching to distribute and manage my servers and my content very efficiently. This is a very cool feature, it's an advanced feature, and is something that I highly recommend that you look at if you can in terms of managing and designing your application environment. We also have something called Global Server Load Balancing, GSLB. This is actually a fairly big and important piece of the load balancing concept. GSLB is not a reverse proxy. It's not the reverse proxy functionality, but it's actually taking advantage of a different technology to give you this concept of availability and scalability. It actually uses DNS, and it's kind of like it's not exactly, but it's like active DNS. So the GSLB, Global Server Load Balancing, what it does is it acts as the DNS server for specific names, like www.kemp.ax. And it's going to look at the different sites which host that name, host that site in different locations. And based on the availability and other algorithms like geolocation, I can direct traffic from clients to one site or the other, active, or in a disaster recovery scenario, as I show in the diagram, to send clients to one site or another based on the DNS response. Send it to this IP address instead of that IP address, and do this actively by managing and looking at those the availability of those IPs and sites. Is a very cool technology. Highly recommended that you look at GSLB technology as you incorporate your load balancing functionality. Another function that you might see is authentication. So you might be doing things like two-factor authentication, token authentication, where you're using these tokens like RSA tokens or other types of tokens to be able to log into websites. Or you might want to authenticate to third-party servers like Active Directory, or or using LDAP or Kerberos, and use that capability to authenticate clients to different sites and take care of that. So authentication, another example is doing single sign-on, where you can do single sign-on to multiple applications to an authentication server. And the load balancer, because it's acting as that reverse proxy, as that first point of connection to those application servers, to those real servers behind it, has the capability to do that authentication beforehand. So this is something that you might see in various load balancing technologies. And last, at least in this case, and there's certainly more situations, but common use cases and scenarios that you use the load balancing technology for, is web application firewall. And this is done a lot because, number one, web HTTPS is the most common application on the internet. And I would actually like to say that, HTTP has gotten to the point where it's not an application, it's a transport, is a method to getting data from point A to point B in one way or another. And this web application firewall is a security technology to be able to protect this web content from various threats and issues. For example, if you have compliance issues, if you're in e-commerce, PCI DSS is a very common standard to protect personal information, credit card information, other types like social security information. So if we see that coming through the system and it shouldn't be, then we can block it. OWASP Top 10. OWASP is a nonprofit organization, and it updates a list on a regular basis called the Top 10. These are the top 10 threats that you're going to see on the internet for web today. And it's updated on a regular basis, and things like cross-site scripting or SQL injection might be on the list, and providing protections for OWASP Top 10 threats, which will protect you from most of the threats and attacks that you see on the internet for web today, is available through the WAF. Or you might have compliance issues, for example, HIPAA. In the US, HIPAA is the healthcare privacy policy where you can only have medical records available to the medical practitioners that care and the actual patients themselves, and you can't leak it out, etc. So you can provide compliance for various policies and standards and things like that, and provide security for protecting the data using this web application firewall. And it's become very popular. Obviously, security is a hot topic, and this is something that you want to consider when you look at implementing a load balancing technology, is to also then look at all these other use cases and functionality like the content switching, the GSLB authentication, and WAF to incorporate into your load balancing technology if it makes sense. So ultimately, at least for me, load balancing is fun. It's really cool technology. I like to say it's not networking, it's not application coding, it's somewhere in between. It is combination of both. It is understanding applications at the network layer is one way I like to look at it. And it's a fairly niche and cool way of understanding and looking at how the network works, how the application works, how these connections and this application experience becomes critical, because that's ultimately what we care about. So look at it as a fun technology, a cool technology that hybridizes and looks at the different model pieces of the OSI model, networking, application, server infrastructure. And of course, let's keep in mind, when we look at load balancing technology, it doesn't need to be complicated. It should not be convoluted. It should not be something that this is this magical black box that does something and you just say, it just works. I have no idea how it works. And if I want to learn, I now have to spend months and go through manuals and manuals and manuals to try to figure out what the heck is going and how this all works. Should not be that hard. So we want to create load balancing technology that should be simple. We want it so that it's easy for you to understand. We want it to be easy for you to implement. So there are a lot of different applications available and used on the internet today, obviously, and they all work differently. So they all should be configured differently to some extent when you configure your load balancing technology. So we want to create templates and models for these commonly used applications to make it easy for you to implement and also manage on a day-to-day basis. And it should be flexible. In today's world with virtualization, cloud, hybrid cloud, software defined, name what you want, software defined networking, software defined data center, hyper-converged, all these various terms that we hear nowadays related to what we call, and I'll put air quotes, digital transformation. It needs to be flexible. It needs to be flexible for you to acquire and deploy. So you want it so that you have licensing where you can do that traditional perpetual licensing where you buy a license for a certain amount of throughput or capacity and you implement it. But you also want the flexibility to say, I want it on demand, so I can have a subscription-based licensing, or even use something what we at Kemp call metered licensing, where you can use the technology and pay for actually the consumption of the technology. Very similar to the electric meter on your house, where the electric meter doesn't care about how many devices you have or how big they are. All it cares about how much electricity are you consuming, and let's bill you for that. So this metered licensing concept is very interesting and it's becoming very popular. You want it to be valuable. You want to have value for what you get. Load balancing technology is not used a lot of times because people say, you know what, it's too hard, it's too complicated, it's too expensive. I can't afford that. But then you have to also think about, can I afford that downtime? Can I afford not having that scalability, that flexibility? But you do need to have value to have performance and functionality, and you need it at a price point that makes sense to deliver that value. So when you compare, for example, in this case, Kemp versus these other competitors such as F5 and Citrix, you'll see a huge value in terms of the cost savings, in terms of the performance you get and the functionality that you get. And the fourth piece, support. I don't expect, or we in the industry don't expect everybody to be a load balancing expert. It's not going to happen. Know what you can, get the basics, understand how it works, but then depend upon the experts. So you need to have a support organization and support that you can leverage to reach out to help you for situations that you need, whether it's your traditional something broke or something's not working right, I need help, or how do I do this? Or how do I load balance my Exchange server in this environment? How do I install in AWS public cloud? And have a support organization that can assist you with their expertise and intelligence that they can. And provide a strong customer support organization is critical. Ultimately, obviously, we think, and I think load balancing with Kemp makes a lot of sense. We have the form factors that you need for your environments, whether it's virtual software running on all major hypervisors, whether it's VMware, Hyper-V, KVM. We have the cloud technology versions, so you can load instances of the load balancer even in the marketplace through AWS, Amazon, or Microsoft Azure public cloud. And of course, if you want the traditional, you can buy hardware-based load balancers, that physical appliance that can sit in your data center and provide that high performance that you need for hardware. We want to make it easy for you at Kemp. We want you to be able to download and play with the software. You can go to our website, kemp.ax/try, to download trial software. And by the way, downloading that trial software comes with full support. So you're more than happy to leverage our support organization for anything questions that you have and help that you need during that trial process, because we know that you're probably not going to be load balancing experts and understand all the nuances. And of course, if you have any further questions or anything that you have about load balancing technology or concerns, please reach out to me. And of course, you can contact us at Kemp at sales@kemp.ax. So that's the presentation for today. And we have some questions, and we have some good questions that I want to go through. And let's take a look at what we have in the list. And the first question is, how does the keep alive factor play a role in load balancing technology? And that's interesting. So the keep alive, I talked about the keep alive with the health checks, where we send well, there's two things. One is keep alive in terms of the health checks. So let me talk about that first, since I'm on that. And the keep alive for the health checks, again, we want to check the health and status of the servers. I said again, for anywhere from 5 to 30 seconds. It can be longer if you want. And if something happens to that instance between those health checks, the system will fail and the load balance will take it out of service. And the general rule of thumb is fail 3 health checks in a row, take the instance out of service. So you have to fail 3 times in a row to take it out of service, usually by default, configurable. So if you set your health checks for every 5 seconds, it'll take 15 seconds for me to take it out of service. And then it'll keep on doing the health checks. And if it comes back up and it passes 1 health check, it'll be brought back into service. So this is adjustable. And the other way that I could look at this question, keep alive factor. So a lot these connection-based protocols like TCP and HTTP can have keep alives to keep the session active, even though there's no traffic going through. So you have what we call a timeout. So if I'm on a web session and there's no traffic passing, eventually that connection table has to clear something out to say this connection is done, because it can't just live there forever. So there's a timeout value anywhere from, traditionally, it might be from 5 minutes, 30 minutes, depending. And again, it's configurable, but you can set this timeout for the sessions for inactivity. And then the applications can send keep alives. Say if nothing is happening, the client might send a little poke to say, I'm still here. I'm still here. And it might send it at certain points. And the load balancer, when it sees that traffic, that keep alive, it'll reset the timer on the timeout for that session to make sure it stays active. So this is the way the load balancer can manage sessions, whether they're active or not active, and also take out inactive sessions. Let's see, the next question. How do I maintain sticky sessions properly between virtual servers and real servers at the backend serving an enterprise application? Great question. So the number one thing is we have that connection table, that 5 tuple that I talked about. So we have a unique source destination IP, TCP, UDP port, and IP protocol. And based on that connection table, unique information is always going to go to the same real server for that instance of the session. There are other things that we can use to maintain stickiness through sessions. And the most common thing, for example, is use what we call cookie persistence. So, for example, in HTTP, we have cookies. They may be a very common cookie is called JSessionID and equal to some unique value. And load balancers can look at those cookies and maintain persistence on those cookies. For example, it can say, since I see JSessionID equal to this specific value, I'm always going to send it to this instance of the server for this lifespan. And if a connection comes back in with that cookie, I will send it back to that connection. Let's look at some other questions here. We have a lot of great questions, and I have a few more minutes to answer some, so I'll try to get some good ones. Is it always good to balance load on network and application layer, and how to decide what to use? Absolutely. Always load balance on layer 4 network, because you have to load balance on layer 4 at a minimum. And do you load balance on layer 7? Absolutely. There are trade-offs. If you load balance on layer 7, you get a lot more intelligence. You can do a lot more creative things. It can be a lot more specific and is better suited in general. But load balancing on the application layer means it requires more horsepower to do it because you're doing content inspection. You're looking at things. You need to figure things out and it takes more horsepower. So depending upon the application, maybe you might say, you know what, this takes up way too much horsepower. I can't afford for the horsepower to do this application load balancing. And then I can drop down to network. But in general, I would try to do application layer load balancing whenever possible. That's my rule of thumb. Be as smart as you can in your decision making. Let's see. What do you do to make sure that the load balancer is not a single point of failure? SPOF. Good question. There are multiple things you can do. The primary thing you can do is you can do what we call HA, high availability. In other words, similar to how I have pairs of routers or pairs of servers or pairs of firewalls working in conjunction, and if one fails, the other takes over, you do the exact same thing with load balancers. You have an HA pair. They share the connection table. So if the primary load balancer fails, the backup will then take over and we'll still have the existing connection table, so none of the connections are lost. So you can provide that high availability, and this is at the local level. So within the data center, if you have a specific load balancer failure because the hardware failed or the network cable failed or whatever the case may be, then you have that HA within the data center or within that local location. And then single point of failure at a global level. Let's look at that GSLB technology, that global server load balancing, that DNS manipulation, where we can now provide availability spread across multiple IP addresses, and they can be redundant in their functionality, in the GSLB functionality, to maintain that high availability so that no matter what device fails from the load balancing perspective, or server failure, or even a data center failure, we can make sure that there's no complete outage for the system. Let's do two more questions here. The first one is, does it use consistent hashing at any point? So hashing is used only in certain cases. So I mentioned in the load balancing algorithms, source IP hashing. Say, take the source IP, do a mod 256, send it to a certain server. And you can actually do hashing not just on a client IP address, you can actually do it on content also. So you can do, for example, URL hashing or other types of hashing. And the disadvantage of hashing is it's very fixed in its distribution algorithm. I'm going to take the hash and I'm going to then map it to different servers. And if something comes within a certain aspect of the hash in a certain value range, say between 32 and 64, I'm always going to send it to this one server. So hashing can be uneven if the traffic is coming from certain locations unevenly. Excuse me. So you need to be careful about that. But you can use hashing in your algorithms. But in general, if you can, and certain applications don't like it, but if you can, using some sort of dynamic load balancing algorithm like least connections does make a little more sense. Last question before I have to end. Can you explain source NAT? SNAT. Source NAT is when the load balancer, in making that connection to the real server, is removing the IP address of the client and inserting its IP address as the source. So that's where the term source NAT comes from. We do this if the application server does not necessarily have a network route or path back to the client, either because of firewalls, network routing topology, things like that. You can then have the load balancer use what we call a source NAT to manage the connection between it and the real server to maintain that connection and ensure the connection and the server can respond back through the load balancer to the client. There are pros and cons to source NAT. The number one con to source NAT is that it hides the client IP address from the application server. For web traffic, this is fixable because we can do what we call header insertion of the client IP address. So we can do an X header client IP address so that the application can know the client IP address. So there are multiple ways we can do this, and there are lots of different things in terms of advanced technologies for source NAT and other pieces. And hopefully we'll create another session and have another session talk about more advanced technologies and capabilities of load balancers. But I appreciate y'all spending the time with me today. Hopefully you learned some great things about load balancing technology, how it works and what it means. And I certainly look forward to you to our next presentations. And hopefully you have a great day. And come visit us at Kemp if you're interested in load balancing technology, because some great things we can do for you. Thank you very much and have a great day.